Hello everyone, I'm Maneli and I'm very happy that you are watching my video today, and I hope you would like it in the end. I want to show you Matlab Simscape capabilities using my own simulation project, which is simulation of a dual-actuated belt conveyor. During this video I will try to demonstrate some Simscape capabilities and also maybe let's say limitations through discussing about some of its blocks. Then we'll see how I use these blocks in my own simulation to build up a belt conveyor system in Simscape environment. So first, let's have a look at a belt conveyor system, its main components and their functions in the system, and particularly how it is operated. In the first slide, you can see three belt conveyor types based on the way they are driven. I just want to show you that the belt conveyors can be and are actually driven in many cases by more than one electrical motor in different stations of the system. Our discussion today is about doubly fed belt conveyors in which they have, as you can guess, two driven pulleys with two electrical motors, and of course you can just put these two stations in different positions of the belt conveyor. In the belt conveyor that I have in mind, the two stations and the two electrical motors are just put at the head and tails of the belt conveyor. As you can see in this slide, we have booster belts, we have power strip. The aim is just to show you that, as I told you, one belt conveyor can be fed with more than one electrical motor in different systems. So, as we just discussed so far, just imagine we have one belt conveyor with, which is fed by two electrical motors at the head and tails of the belt conveyor. The question would be how these two motors should interact with each other so that the belt tension, which is one of the most factors of one belt conveyor, remains in acceptable range, both in steady state condition of operating and also during the startup phase. Also, it is really important for the operators to be able to start the belt conveyor in a mechanically smooth way. Of course, it is also important to feed the required energy to the belt conveyor in a fair manner. It means that both the electrical motors just cover up half of the required energy. For the questions and the challenges I just mentioned, there are some practical ways in today's industry. One remedy or one approach is to drive the belt conveyor using the hydrocouplings between the electrical motor and the, let's say, load, which is our belt conveyor in this case. The hydrocouplings will just give us the capability to start our belt conveyor mechanically smooth, and this way the stress on our mechanical parts will be reduced really significantly. But the challenge, which would be just setting the belt conveyor speed and to control the amount of bulk material which is just carried by the belt conveyor remains unanswered, because the hydraulic couplings do not give us any ability to control the belt conveyor speed. So if you really want to have everything under control, you need to use frequency converters for your electrical motors. If you have the frequency converters, you can just start the electrical motors completely under control from speed 0 to your operating speed in a timeline which is completely under your control. You can start the system so fast, or you can give it time, and this way the belt conveyor will start up so smooth mechanically, and also at the same time you have the operating speed under your control. But of course the frequency converters will be much more expensive than hydraulic couplings, and of course they are let's say more complex systems. Of course, if you can have as many as motors and frequency converters for one belt conveyor, you can go beyond 2 stations, and this way you can cover up and then you can feed the huge belt conveyors which are as long as several kilometers, and you will not be worried that the energy consumed by the belt conveyor is so huge that cannot be fed to it in just 1 or 2 stations. But of course, the more stations you have, it becomes more important for you to have some remedies and approaches to make sure that these different stations interact with each other in a smooth way, and energy is given to the belt conveyor from the electrical motors in a fair way. We have mainly 2 approaches in practice to design the interaction between the head and tail frequency converters. The first one is called master-slave approach, and the other is to make a small difference in head and tail speed set points. The first approach, master-slave, focuses on the torque that is coming out of the master motor, and then this torque measurement is done in each moment, and then in the very same moment the system calculates the rest of the required torque, which should be fed to the system by the slave motor. So in this master-slave approach, the master frequency converter is responsible for controlling the speed of the system according to the set point from the operator. At the same time, it just feeds a portion of the torque required for the system, let's say 50% of it, and the slave follows the master, supports the master, and just covers up for the rest of the 50% required torque, and this second portion is just supplied by the slave motor. The second approach, as I told you, is to make a difference between the speed set points of the master and the slave. This means one leads a little bit, and while the other one lags a little bit. The tension alongside the belt, and as well as the maximum tension of the belt conveyor, is somehow proportional to this difference between the two motors and their set point. If this difference is too big, then the tension on the belt conveyor will grow proportionately. So we need to know how much tension we want to have on the belt, and then we can decide how much difference there should be between the set point of the head and tail set points. Of course, too much tension will damage our belt conveyor, as I told you before. On the other hand, if the tension is too low, then you don't have any friction between the driven pulleys and the belt, so no force is exerted to the belt and no motion is created, which is not desired at all. So to model the belt conveyor, there are several components that must be present in our simulation. The head and tail pulleys, here you see them at the two sides of the belt conveyor. The pretension weight as well as the belt material itself have to be modeled. As you can imagine, the belt pulleys, which are both driven pulleys in our case, are just cylindrical shape parts made of steel, and using some solid blocks we will model them in our project. Also, the belt material, the main character of the belt material is its stiffness, so we need to model the belt material with some springs as shown here. Simscape has spring blocks already which can be used for this purpose. The other part that I named that has to be modeled is the pretension weight. I will explain about this part later when we go to the Simscape project. There's a list of the Simscape blocks that we're going to use in our simulation and in our modeling. The list starts with cylindrical solid, which is obviously going to be used for modeling the head and tail pulleys. We have brake solid, we have general flexible beam, we have revolute joint, we have prismatic joint, we have spatial contact force, and in the end we have transitional spring and damper, which will be used for the belt material. The belt conveyor system we are going to build inside the Simscape will become something like this. The good thing about the Simscape environment is that it gives you some isometric view and also other views from any side that you need to see your model. Here we have two pulleys, head and tail, in different colors. We have this pretension weight, which I promised to explain about later, and we have also the belt material itself. As you can see in this view, the belt material is not in tension at the very moment. It's a little bit slack, so you can imagine if we exert some torque to either of the pulleys, as there's no tension on the belt material, most probably the pulleys will start rotating without having any tension on the belt. There will be no friction between the pulleys and the belt material, so the belt will just stay where it is and no motion will be created on the belt. That's where this pretension weight starts playing its role. But still you need to wait a little bit. We will go inside the Simscape environment in some seconds, and then little by little you will understand the role of this part in more details. Once you open the Matlab software in your computer, you will face such a window. Here you can go to Home tab and then to Simulink. Inside Simulink environment, you can choose a blank model to create a model from the scratch. Here the first thing that is going to be needed is to somehow import the blocks into our model. We already talked about the blocks that we are going to use in this project. Here I just show you some two approaches. The first one is just to simply make a double click and type what you need. For example, I need a transitional spring block. I simply type the word spring. A relatively long list is shown to me, and it just contains the blocks with the name spring. So I just go straight ahead to transitional spring, enter, and then I have a transitional spring in my new model. The other way would be going to library browser. Here you can also search just almost as the same as I just showed you. Again, I just type the word spring. The search just starts for me, and here in the right side of the library browser you can see every kind of spring block available in Simulink library that can be used. It is very important for you to know that not all the blocks that are shown here can be visualized by the mechanical window. Later I will show you the mechanical window, but just be noted that if you want to visualize your model in the end of the project, and you want to just see the different parts interact with each other, then you have to just choose the blocks that have this ability. Anyway, here you can see a long list of libraries. Each of them has some blocks inside that can be used, but among these, of course, it is just the Simscape library which is of interest for us in this session. As you can see here, we have this Simscape library. Inside it there are several categories: foundation library, utilities, driveline, electrical, fluids, and multi-body. I'm just opening some of them for you to see what is going on inside them. Here we have, for example, body elements, different beams, flexible bodies, and so on. Now that we know how to insert different blocks into our model, I just opened my own project, which is, as you can see, already filled with very many blocks. Here I just want to show you every and each part of my project, and I guess this will be useful for you to create your own new projects. Once you want to model any system, you will need these blocks, and hopefully my explanations on each block will help you for your new project. I just want to start with the very 3 blocks that every model will need. The first one is called the solver configuration block. This block is responsible for the mathematical job that has to be done in every simulation. Every simulation just results some differential equations, and they need to be solved so the simulation is finished. This solver configuration is responsible for this mathematical job. The second block is word frame. The position of all the blocks that you put in your model is given with reference to this word frame, which is orthogonal and also motionless. The third block is mechanism configuration. By double clicking I can see all the parameters that I can configure in each block as the user. In the case of the mechanism configuration, it is the gravity of the environment that you are creating that can be set. Here you can see that the gravity is equal to 0 in all the 3 aces. The unit of the gravity can be chosen here. For me it's the metric units that I want to use, and for the time being I just leave the gravity to be 0. Just be noted that whenever you want to start a new project, you don't need to think about anything. Just in the first step, insert these 3 blocks in your system, and then every block that you want to add to your system and to your model have to be connected somehow to these 3 blocks. Then of course it is important to visualize what you are creating so that the user job becomes really easier. To visualize what you are creating, you just need to use the shortcut Ctrl plus D. Once you do that, the system just compiles what you have created and opens a new window which just visualizes what you have created. So as you can see, the system is right now compiling my system. Here, as I already told you, you can have this isometric view of the system, and then using your mouse wheel you can just rotate it and see it from different views and sides. Here at the top you can just also set new views from different sides of the system. Here, for example, from the top, this is the view of our belt conveyor with the width of 2 meters. I will later show you how I made it 2 meters, and of course it could be 1 meter or anything that was required. So I just want to show you different views. You have somehow 2 windows. For each you can select its own specific view, as you can see. Also at the left side, as you can see, this is the complete list of all the parts and blocks that I have used inside my model in the Simulink environment. They all have some unique name, and if I just click on any of them, I can see the visualized block inside the other window. For example, here I just choose S13, and it just shows me that S13 is this one here, which is a solid block. Then I can choose S14, and then I can easily see that this is S14 here inside the visualized system. So here I can choose how many visualizing windows I want to have and how many views I want to see simultaneously. So if I just need one, I click here, and one view is shown to me. Here I can just choose how I want to configure this single view. This one here gives me the isometric view, which is very useful. I can also divide my screen into two views. Here I select the top one and make it like this. Here I select the below window and the isometric view by clicking here. It's chosen for this view. Here I can also see the directions. This is just the word frame I already talked about. You can see the Y, X, and Z. And if you remember, it was possible for me here in the Simulink window, inside this mechanism configuration, to set some gravity in the direction I wanted to have. So the way I have just put my model parts is just showing that I need the gravity to be in direction of Y. As you can see here, this is Y, the green line, and obviously I need the gravity to be downward, which is the in Y direction. So if I want to have gravity, I can just put it here. For the I change this 0 of the y-axis to minus 9.8. So now my word frame has some gravity in the direction of y-axis. The next thing to do is to just add some parts to our model and visualize it. Here, for example, I already have this part. I just copy and paste it inside my model using shortcuts Ctrl+C and Ctrl+V. I just copied two of it. But it is important to know that just bringing some block inside the model doesn't mean it will be visualized. Here, as you can see, I just added two parts. I just use Ctrl+D to compile the model once again, and then we will want to check if our visualization has changed. So it's just the same as before. I use the isometric view, nothing new is added, although we just added two blocks here. What we need to do is to give these blocks some reference of position. So this R, which is the frame of this part S31, should be connected to the word frame. I just connect it like this. Now again I compile the system using Ctrl+D. And we can see the result here. Now let's add one break solid to our system to see what happens. Break solid, here it is. So if you open the break solid parameters, you can see that it's shaped like this by default. As the name says, it's a solid part. For example, if you need to show some parts which is made of steel and has some rectangular shape like this, you can use this block. Here in geometry you can change its dimensions. For example, this is 1 meter in every side. You can just change it to 2 meters in all sides. So now it's just 2 meters. I changed 1 parameters. Now it says I need to push F5 so I can see the result. I can use the wheel mouse to zoom in and out. Again, here I have very many views to choose from. The most useful one is isometric view, as you can see here. I can even make the dimensions to centimeters, and then again F5, and the result is like this. So basically I just make some solid parts by this block. I just put it like this, 2 meters in every side, and I just update the visualization here. And here of course you can just configure what density your material has. Again, the units of the density can be chosen based on what you wish to see here, or you can just choose the mass menu and specify the mass of the break solid that you have created. Of course, either you need to choose the mass basis or the density basis. For me it's here now density basis. You can just go to the graphic menu and change the color if you want to make differentiated from other blocks that already exist in your model. So I just want to change the color so we can see what changes this single part is going to make in our model. I just change the color to yellow and click OK. So now we should have a new part in our model. Let's use Ctrl D to compile the new model and see if we can find any changes in our model. So here is the updated model. I cannot see any yellow part added to it right now, so it seems nothing is added. As I told you before, we need to get every part we create connected to the world frame. So I just drag the R frame of our part and connect it to the world frame. Again, Ctrl D, and the system compiles the result. Now something should be changing in our model. Here's the result. This rectangular shape is added to our model. So what if I want it to be somewhere else? Or what if I want it to be 2 meters away from the position it has right now? Then I have to use another block which is called rigid transform. Again, double click, rigid transform, and here it is. This block adds nothing physical to our no physical part to our model. It just gives us some reference and gives us some new position in reference to the world frame. So I just connect one of it has basically two frames. One is supposed to be connected to the new part, and the other frame is supposed to be connected to some already existing part or to the world frame. I just get it connected to the world frame in one side, and in the other side I get it connected to our new part, which we chose to be yellow. Here I can go to the translation or to the rotation menu. Here we want to just set some new position to our new part, so I go to the translation menu. I choose the Cartesian method, and here you can see I can set some new position for the part by this three-member matrix. I can just move it forward 3 meters in every side. Here, as you can see, the unit is meter. It could be centimeter, millimeter, or anything else. Apply, OK. So now Control D to compile the changes and to visualize what we have created. Now, as you can see, our new part has moved away from our already existing belt conveyor. I suppose this distance is somehow 3 meters. Of course, I mean the Cartesian distance in every axis. Now that you have seen the function of rigid transform as well as break solid, we can go to other blocks of Simscape. Every time that two parts in your model have motion in relation to each other, it could be rotational or translational movement, you need to use some joints. There are very many different joints available in Simscape. I just type the word joint to see what we have available here. As you can see, joint space mass matrix, joint space motion model, 6 degrees of freedom joint, planar joint, bearing joint. Among all of these, what I have used in my model are revolute joint as well as prismatic joint. I just want to show you my belt conveyor again. If you just notice here my belt conveyor material, which goes around the two pulleys at head and tails, you can see that it consists of actually very many solid brakes. All of them have 2 meters width, but they are small in length, and also they are small in thickness. So somehow I tried to model belt material using a small, very small bricks, very many of bricks alongside each other. But these bricks will have two motions once the belt conveyor starts operating. One is of course the translational movement. The other one is when the brakes just come to the cylindrical solids, which are our pulleys at the head and tails of the belt conveyor. As you see, they have some rotational movement in relation to each other. So here between each two brakes there should be some kind of revolute joint, which just makes it possible for us to see that the two solid brakes just have a rotational movement in relation to each other. What I did inside my model is that I inserted very many solid brakes, as you can see here, S1, S2, S3 and so on. They are all the same in the shape. Of course I needed them to be placed alongside each other to get them in right positions. As I already discussed about the position, I used some rigid transformers, very many of them. These rigid transformers just helped me to place the solid brakes alongside each other in some lines, as you have seen inside the visualization. Between each solid brake there are two revolute joints. These are the joints that make it possible for the brakes to rotate around each other. Now I want to just make a smaller model consisting of two solid brakes to show you how these revolute joints actually work inside Simscape. So to show you how the revolute joint acts in our models, I just created a new model, a very small one consisting of two brake solids, S1 and S2, as you can see. As I told you, just without any hesitation, I always copy and paste these three blocks in every model: the solver configuration, the volt frame, and the mechanism configuration. The mechanism configuration does not have any gravitational force. They are all zero. Let's see the result for now. The system is compiled, and as you can see, it is visualized here. It consists of just two brake solids, S2 and S1, which are placed alongside each other. This position is created by help of these rigid transformers, as I demonstrated before. But now let's we can just run the simulation here in our mechanical visualization. I just play the simulation. As you can see, it just goes on and nothing happens because there exists no force which is exerted on our two parts. Now let's add the gravitational force to our model here inside the mechanism configuration. Just add some gravitational force, 9.8. So I compile the model again. Nothing seems to have changed. I just run the simulation again. Now you can see that the two parts are able to rotate in relation to each other and also in relation to the volt frame. This degree of freedom is achieved using these revolute joints, which are between part S1 and the world frame, and then these two revolute joints which are placed between S2 and S1 parts. So these revolute joints are just giving us some very limited degree of freedom, which is the rotating freedom for these two parts, as you just saw. The force which just causes this rotation is the gravitational force that I created in my mechanism configuration. Let's go back to our mechanical visualized model, our belt conveyor system. So far we discussed these brake solids. We have very many of them in our model, just placed alongside each other. We discussed about the revolute joints between these solid brakes. What we did not discuss so far are these three cylindrical shapes. As you already know, these two bigger cylindrical parts are the two head and tail pulleys of the belt conveyor, and this little one here is the pretension weight. As you can see, and I already talked about this matter, the belt conveyor, which is the belt material around the pulleys, is not under tension at the very moment. Just before we start exerting some torque to our pulleys, and just before we start the belt conveyor, we need the belt material to have some friction against the pulleys, so that when we rotate the pulleys, the belt also starts moving. To create this tension, this initial tension, let's say, we need this pretension weight, which will just drop down because of the gravitational force, and will give us some pretension on the belt material. But the thing is that the movement of this pretension weight should be limited to upward, downward, and it is not supposed to be moving horizontally. Again, just like the case of revolute joint, we need some suitable joint here which gives us the degree of freedom that we require, and at the same time limits the movement of the pretension weight in the directions that are not desired. But here the movement is somehow linear and it is not rotational anymore, so the type of the joint we need here is the prismatic joint. The prismatic joint is just used here in my model. There are very many parameters that are common between different types of joints. They just have other functions too, other than giving us some degree of freedom. They have also they can actually play the role of actuator. They can exert some force or some torque on the joint also. So if for example you need some rotational freedom, you use some revolute joint, and at the same time if you want to exert some torque on this revolute joint and make it rotate, you can just parameterize the related parameters which are here shown in which are listed in actuation menu, and then you can enjoy the result. Here, for example, you can set some torque inside the system. The torque source could be some other block outside the joint which gets connected to the joint. So in this case you just click on provided by input, and then one extra input is added to your revolute joint, or it could be automatically computed. In this case the joint just responds to the torques that it receives in interaction with other parts of the model. In case of this prismatic joint, which was our primary topic, I just, as you can see, have chosen the provided by input menu. So here, as you can see, I have one extra input which is called f, small f. Here I can just use this constant block to exert minus 100 Newton force to this prismatic joint. And this 100 Newton force will be exerted on my pretension weight, which is here connected to this prismatic joint. This force from this constant plug will be exerted to this pretension part, and will just move it downward so that I can have some initial tension on my belt conveyor even before getting it started by the rotating pulleys. It is important to notice that it was also possible not to use this block and this force here, because the gravitational force that I already configured in my mechanism configuration just gives me enough force to move the pretension weight downward. So either this gravitational force set here or the constant force set here, which is exerted directly to the prismatic joint, any of them is enough for me to get the initial